Okay, so far we've talked about real zeros, and now we have to talk about the complex zeros. Okay, so our objective today is to use conjugate pair theorems and find all complex zeros of a polynomial function and write polynomial functions when you're given zeros. Okay, so complex zeros are ones that don't show up. Okay, so first of all, we have to look back at the rational zero theorem to see what it really means to have complex zeros. Okay, so there are some limitations to the rational zero theorem. For example, if you have a function like this, and the rational zero theorem, it tells you, oh, you have to find all the possible roots. That means you have to find the factors of this guy and the factors of that guy, and then you try them, and it comes out that you have two that works in this particular function. Okay, so these two work. So then you have the factors of 3x plus 1 and x minus 2 from these guys. These zeros give you these factors. Okay, but um, sometimes they don't always work, right? They don't work all for all zeros because there are some zeros that are hidden. So the limitation of the rational zero theorem is that it can't find you all the zeros. It only finds the rational ones. Okay, so um, if you go through the same process here, your possible roots are positive -1 and positive -2, and you try them. The only one that works is -1. Okay, you see how you should have a lot more zeros, right? Because this is pretty high order, third order, so you should have more than just one zero, but only this one works. So what that means is your function factors to be x plus 1 from, see, the x plus 1 gives you that 0. And then this pink guy here, this guy, the zeros are hidden in this guy, and you couldn't find that with the rational zero theorem because it's not rational. Okay, because if you look at it, you really you solve for that, you should get something here and here, and these numbers are not rational. That's why you couldn't find it with this theorem. That's the limitation of this rational zero theorem. Okay, so what we have to do is move on to a new theorem called the fundamental theorem of algebra. We call the FTA for short. Okay, so what it says is every polynomial of degree n that is larger or equal to 1 can be factored into n linear factors of the form this. Okay, so what does that mean? Okay, so you guys got to really learn how to read these definitions. So it's just saying the polynomial f, or any function really, if it has degree of 1 or larger, then you can make that many factors. Linear factors mean first degree factors, like there's no power on x. So it's just x minus a number, x minus a number. So what it really means is that if you have n degree polynomials, then you got exactly n roots. Okay, so if you go back like before, right? So here you find that the third degree, you only found 1 0, but really there should be 3 zeros. Okay, and this theorem tells us that. So here it says if you have n degree, you can find n roots. Okay, some of them are complex though, meaning that they are not all real roots. So the rational zero theorem can only find you rational ones. That means they're only part of the real ones. So some complex ones don't show up with the other theorem. So what can we do with this theorem? It's going to help us find all the zeros, basically. Okay, but we'll get there slowly. So here's an example. How do you find all the zeros of this guy? Well, just know that this is second degree. You got to have 2 zeros. Maybe not both of them are real, not both of them are rational, but some might be complex, some might be irrational. Okay, so to find a zero, this is second degree, so we know how to do that. We know how to deal with second degree. So you just set that equal to 0, and then you solve for it basically, right? So subtract 2 and then square root both sides. You see that I have square root of 2i and I have negative square root of 2i. Okay, so because I square root both sides, so I have positive and negative square root of 2i. And I, because it's a negative, you square root a negative number, you have imaginary. That's what makes it complex. Complex just means that it has imaginary parts in it. So here I found two zeros. Okay, so f of x is really just x minus 2i times x plus 2i. But these numbers are complex. Right? If you multiply them together, you get back this, basically. You get back to the original one. All right, so um, immediately from that, you can see a theorem that we call the conjugate pair theorem. And all it says is if a plus bi is a zero of a polynomial function f, then the conjugate a minus bi is also a zero of f. Basically, it means that if you have imaginary root, then you have another one that is just the negative of that. Okay, like how you saw here, positive 2i and negative 2i, they come in pair. Okay, so here, let's look at an example. You have a polynomial function f of fifth degree, right? Degree 5 has a 0 of 1, 5i, and 1 plus I. What are the other zeros? Because so if you look at this, 5 is a real zero, it has no conjugate. But 2i is a complex zero, and its conjugate is negative 5i. Okay, so they come in pair. If you have 5i, you got to have negative 5i. And you have 1 plus I, then 1 minus I has to be also in there. So now you have 5 zeros, right? So the zeros are 5, 5i, negative 5i, 1 plus I, and 1 minus I. Okay, so just know if you have a complex zero, there's another one in there that's negative of that. All right, so here, another example is to write the function when they gives you the zeros. Okay, this one is really, it's hard algebraically. That means that you have to do a lot of manipulation. So if you guys are not sure on how to do complex numbers, multiplying complex numbers, just look up a video on how to do complex numbers. Okay, but here they give you the zeros here, right? This is fourth degree, and they give you 3 zeros. So there's got to be another one. But you see, these guys are real. They don't have conjugates, right? This one is the imaginary one. So you have negative 4 plus I. The other one missing is negative 4 minus I. So here I have that written down. 1 is a real 0, so no conjugate. Negative 1 is a 0, no conjugate. But negative 4 plus I has a conjugate, which is negative 4 minus I. So now you have 4 zeros, right? So your function looks like this. X minus 1, x plus 1 from these two, and then x minus negative 4 plus I, and then x minus negative 4 minus I. Then all you got to do is multiply these together to get standard form. So I multiplied the first two, x minus I, x plus I. That's a special pattern, right? X minus a, x plus a gives you x squared minus, a squared. So I have x squared minus 1. Hopefully you guys remember that pattern from Algebra 2. We did that last year. And here I'm going to simplify the x minus 4 to be x plus 4, and then minus I. Okay, this became this. X minus negative 4 is x plus 4. And then minus I right here. Okay, in the back I have x plus 4. And then minus negative I becomes plus I. So I'm going to group these in such a way that I have x plus 4 together and x plus 4 here together. So you guys see a special pattern. Again, I have x plus 4 and x plus 4, minus I and plus I. So that's a special pattern that gives you x plus 4 squared minus I squared. Just like here, you have x squared minus 1. Here you have x plus 4 squared minus I squared. And minus I squared is just negative 1, right? I squared is negative 1. So I have, and then I multiply the yellow part out, x squared plus 8x plus 16 minus negative 1 from I squared, which becomes plus 1. So then I have x squared plus 8x plus 17. And then I multiply all this out again. Again, guys, this is just all really just algebraic work, right? And if you're confused with any of the steps, review or ask questions. I can go over some of these problems in office hours or in class if you guys need me to. Okay, just ask the questions. And I just multiplied all this out, foiling basically, but with more stuff. And I FOIL that out, I get that. Okay, and that is my function. And if they give me a point, I can actually find a. But I don't have a point, so I'm going to leave it as a. Okay, so let's look back at this here. There is something that we can conclude from this, right? So imagine if you have a fourth degree polynomial, okay, fourth degree, you can have four real zeros and no imaginary zeros, right? Or complex zero. Because fourth degree got to have four zeros. If all four are real, then no imaginary, no complex. If can you have like one real and three imaginary? You can't have three imaginary because they come in pairs, right? So you can only have two imaginary or four imaginary. So you can't have that. So you got to have two imaginary and two real. Or you can have four imaginary and no real. Okay. Now look at the fifth degree. You can have five real and zero imaginary, or two imaginary and three real, or four imaginary and one real. So what can we conclude from this is that if the degree is odd, you always have at least one real one. Okay, you can always have at least one real zero. So that's the conclusion that we can draw from that, right? Odd degree polynomials have at least one real zero. So let's do a couple examples here. Actually, I'm going to do one only because it's really long. I'm going to keep this video relatively short. So here they want you to find all the zeros of this polynomial. So I have listed the steps for you. Okay, step number one, use rational zero theorem to find all the possible zeros. Again, some of you guys are still confused with the steps. I'm going to do this out slowly. So I'm going to find all the factors of 3, which is 1 and 3. All the factors of 18. Oh, that should be 18, not 3. Are 1, 2, 3, 6, and 18. Okay, so you take each of these and put it over each of these. So I have 1 over 1, right? Which is 1. 2 over 1, which is 2. 3 over 1, which is 3. 6 over 1, 18 over 1. And then I'm going to do 1 over 3, which is 1/3. 2 over 3, which is 2/2. 2/3. And then 3 over 3 is 1. I don't need that. 6 over 3 is 2. And 18 over 3 is 6. So you see how I have these, right? This is 1 over 1, 2 over 1, 3 over 1, 6 over 1, 18 over 1. And then 1 over 3, 2 over 3. And then 3 over 3 is 1. I don't need that. 6 over 3 is 2. It's already here. 18 over 3 is 6. It's already here. So these are my possible ones. And then step number 2 is to find the a real zero by testing them. Remember, try easier numbers first. So I'm going to try 1. And it doesn't work when I plug 1 in because I got 60. I need to have 0. I'm going to try -1. It also doesn't work because I got -40. I move on to 2. I'm going to try 2. It doesn't work. It gives me 260. And I'm going to try -2. And this one gives me 0, so -2 works. -2 is a 0, so x plus 2 is a factor. So what that means is f of x is equal to that. And x plus 2 is a factor times something. So f of x is equal to this, which is x plus 2 times something. And I need to find out that something. Okay? That something here is the new thing that I need to factor. So to find that, I take f of x, the original one, divide by x plus 2. So I use synthetic division. And here, see, I should get 0 as the remainder because it goes in evenly. So when I do synthetic division, the result is the red stuff. So 3, -1, 27, -9. So I have that right there, okay? So once I've found out what the red guy is, I can move on to the third step, which is to continue trying to break down that red guy, going back to step number 2 by trying the numbers again, or I can try factoring. And I suggest always factor, right? A factor is easier. Try factoring first. If it doesn't work, you can go back and do the trying the numbers again. Okay, but I'm going to factor, and luckily it works, right? So what it does is I'm going to take out the common factors from the first two guys, which is x squared. So I take x squared out, and I take 9 out from the bottom, the last two guys. Okay, so what I have left is 3x minus 1 from both of them. So that gives me x squared plus 9 times x squared. 3x minus 1. So now these are factored. So what that means is instead of that becomes these guys. So 3x squared plus 9, 3x minus 1. Oh, there should be a 3 there, by the way. No 3 there. Just x squared plus 9. So from these guys, I just find zeros from that, right? So the last step is to find the rest of the zeros once you have all the factors. I have all the factors. So I have 3x minus 1 is a factor. So I solve for that, right? 3x minus 1 is equal to 0. 3x equals 1. And x equals 1/3. So that's how I get 1/3 as a 0. And then this guy here, again, there shouldn't be a 3 there. Just x squared plus 9 is a factor. So I solve that x squared plus 9 is a factor. I have x squared equals negative 9 and x equals 3i and negative 3i. Okay, so I have 3i and negative 3i as my other zeros. So a total of 4 zeros, because this is fourth degree, right? I have negative 2, 1/3, 3i, and negative 3i.